So we are finally at naming cycloalkanes. We're going to learn how to deal with naming cyclic systems when it comes to alkanes, known as cycloalkanes. And we're also going to discuss a couple of other points, such as what happens when there's stereochemistry involved. This is the wedge and dash type of formation you may have come across in your class. And then we will also talk about what happens if we have a cycloalkane and a carbon chain that is of significant length, and the two of them are kind of competing for the parent chain. How do we know when the cycloalkane is the parent chain versus when the straight end or open chain is going to be the main parent chain? So a couple of notes first. When a parent chain is in a cyclic form, it's going to use the prefix cyclo. So if you have a six-membered ring, it's not just called hexane, because that would be the straight chain version. It's going to be referred to as cyclohexane or cyclopentane if it's a five-membered ring. Okay, now keep in mind you can't go lower than a cyclopropane, which would be a triangle, because once you only have 2 points, you can only make a straight line. So there is no such thing as a cycloethane or a cyclomethane. Now when you're numbering a ring, this is a little bit different. There are no terminal endpoints, right? So when we normally number carbon chains, we start at 1 point and we go 1, 2, 3, 4, and we go all the way up through until we hit the other end that we determine to be the longest carbon count. And when you're in a cyclic form, there's no start or end. It's just roundabout when we do that. And because you have no terminal endpoints, you, as the viewer, will decide where the optimal placement for number 1 begins. And it can be anywhere in the ring, provided you're following Rule 2 and implementing it. So a substituent or another functional group essentially should always be found in some position 1, right? Because we want to give the lowest possible number. So if I can pick any position and start it as position 1, I ideally would then be starting my position 1 at one of the substituents, because Rule 2 says I give the lowest possible number to all substituents, so 1 would be the lowest possible number. So let's take a look at a couple of predetermined examples here that we're going to work through. So on the left there, you see just a cyclic compound. That's a 5-membered ring, so it would be called cyclopentane. Now take a look at the middle one. This is interesting. It's methyl cyclohexane. So we know cyclohexane is going to come from the fact that it's a 6-membered ring, and there's a methyl group attached to that ring, but there's no number 1 associated with this. It's not 1-methyl cyclohexane, it's just methyl cyclohexane. And the reason behind this is that there's an implied 1 that's already there. If there's only one substituent on a ring, there's no need to number it because it's inherently going to be the number 1 position. It's always going to be number 1. So we don't really need to state that. Now, why is this not the same case with an open chain? Well, first of all, if you have a methyl group on the end of an open chain, it just adds 1 additional carbon to the main chain. And the open chain has many positions in the middle that can have a different number. So 2, 3, 4, etc. You have to tell the user where you want that methyl group. If it's on a cyclic compound, I could put it on any of the 6 points and it's the same compound. It's going to be identical. I can just rotate it around however I want. Now, look at the next example over on the right. We've got an ethyl group and a methyl group. We obviously want one of those groups to be position 1, and the other one is going by default to be position 3. So then we could have a 1-3 or a 3-1. We go back to one of the initial points that we talked about in the rule lecture videos, which is that when we get ready to number and we have to combine it with alphabetizing, and it doesn't matter, we can reverse it forwards or backwards and it's the same, the one with the higher alphabetical priority is also going to get the lower number priority. So in this case, ethyl comes before methyl because E comes before M, and so therefore on the cyclic compound I'm going to give the ethyl the 1 and I'll give methyl the 3, and that's simply because of the way that they are organized alphabetically. So then the name for this becomes 1-ethyl 3-methyl cyclohexane, right? So 2 major points here. Number 1, you're now going to put cyclo in front of your parent chain. And number 2, you are going to start numbering from wherever the optimal place is. You're no longer stuck with having to number at one end of a chain versus another. So those are 2 major differentiations that come about when you're dealing with cyclic compounds. All right, now a few minutes ago we mentioned that you could have some sort of stereochemistry. So we call it wedges and dashes, right? It's really out in front of the plane or behind the plane of the molecule. And we're talking about plane as in a dimensional plane. So many times you're going to see wedges and dashes, and that's telling you about the stereochemistry. If you see 2 of them that are in a repeating pattern, meaning I either see 2 wedges or 2 dashes, it can be either of those, that's going to refer to something that's cis, and that term means on the same side. So if I've got 2 wedges, for instance, it's saying that whatever group is on those wedges, chloros, methyls, ethyls, whatever it might be, they're on the same side of the cyclic ring. They're facing the same way. And then if I see an alternating pattern, a wedge and a dash and a wedge, that means that it's going to be the trans isomer, and the trans means on opposite sides or opposite of. So take a look at these examples here. Okay, on the left we have a cis isomer, and on the right we have a trans isomer. And these technically are 2 different compounds. Even though they are both 1,2-dimethyl cyclohexanes, one of them is oriented on the same side, one is oriented on a different side. And this gets into a little bit past the realm of naming when we start dealing with, stereoisomers, stereoconformers. That's going to be its own lecture series when we get ready to talk about, maybe you've heard of R and S and cis and trans and chair conformers and all that type of stuff. What we really want to focus on here is with the naming, if you see these types of patterns, you're going to do cis if they're on the same side and trans if they're on opposite sides. And you just put that in front of the group that is cis or trans. So in this case, it's the 1,2-dimethyl. So it's cis 1,2-dimethyl. And in the other case, it's trans 1,2-dimethyl cyclohexane. Okay, and then finally, one of the other things that we mentioned at the beginning of this lecture, when is a cycloalkane going to be considered a substituent, and then when will it be considered the parent chain that we would utilize for naming? Because you could have a case where you have a larger chain, not just a methyl or an ethyl, and then you might be confused, well, is this a cyclohexane or is it a heptane, or something of that nature? So the answer here is that you count the carbons on the ring, and then you count the carbons on the chain leading up to the ring, but not including that first point on the ring. Okay, and the larger count is going to win the title of being the parent chain. And if the cycloalkane is not the parent chain, it becomes a substituent and it is named as such. So let's take a look at 2 examples here. Okay, so on the left, you can see where the case is made for the cycloalkane being the parent chain. So if I were to come over here and I were to count, I would say 1, 2, 3, 4, 5. So I have 5 carbons associated with the open chain portion of this molecule. And then when I come over to the cyclohexane, I have 1, 2, 3, 4, 5, 6, right? Because it's a hexane. So 6 is greater than 5, therefore it's a cyclohexane and not a pentane. So what do I do with the pentane? I call it pentyl. Again, I don't need to say 1 pentyl because there is only 1 substituent here. Now if there was a methyl somewhere else on the chain, then I could get involved in numbering and saying, 1 methyl 3 pentyl or something of that nature. Now, moving over to the right, when I take a look at what I see on the right over here, I now have a longer chain than I do a cyclic compound. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. And then we obviously have 6 associated with the cyclohexane again. So 8 is going to be greater than 6, and therefore the open chain format will now take precedence as the parent chain. And this is going to be an octane instead of a cyclohexane. So how do I name the cyclohexane in relation to that? It becomes cyclohexyl. Okay? Now, why do I need a 1 here? because the cyclohexane is not the main chain at this point. So don't get confused. We're back with having a straight chain, an octane. And I numbered this backwards because I wasn't numbering it for the purposes of naming here. It was just to differentiate the numbers. But you would number it as a 1 here, right? Because that would give the lowest possible number to the cyclohexane. And because this is an open chain, it's 1 cyclohexyl, because I need to identify where it is. It could be 2 or 3 or 4 cyclohexyl when we're dealing with an octane chain. I need to tell the user where I want that cyclohexyl, right? Because if it was 2, I could create an octane again, 1, 2, 3, 4, 5, 6, 7, 8, and then I could come 1, 2, let's say 3 in, and I could go ahead and put the cyclohexyl there. So now if I were to number this, 1, 2, 3, 4, 5, 6, 7, 8, right? This is still an octane. However, now it's a 3 cyclohexyl octane. It is not just a 1 cyclohexyl octane. So again, open chained format, the numbers matter. You need to have the numbers there, even if it's only 1 substituent. When you get to the closed cyclic form, if there is only 1 substituent, like we saw on the left, you can omit that number because it's inherently going to be 1. So I just wanted to point that out so that people weren't confused and said, hey, you have a cyclic compound, why did you need the 1 there? Because this cyclic compound is now the substituent. The octane is the main format. And so if I'm going to use a parent chain that is open format, then I need to make sure that I include the numbers to differentiate where that substituent is popping up. That really takes care of the cycloalkane lecture and all the points I want to address with that. So we will continue forward. We're getting pretty close to the end of the course, so keep up with it, and then we will get ready for some practice sessions so that you can implement all of these skills that we're learning. I will see everybody in the next lecture.